Previously, we gave an alternative characterization of the hyperbolic plane. A binary quadratic space is isometric to the hyperbolic plane if and only if its discriminant is congruent to -1. In other words, it's minus of a square. In this video, we give another characterization of the hyperbolic plane. For a binary quadratic space, V is isometric to the hyperbolic plane if and only if it is isotropic. Remember, this means that there must be some non-zero vector in V such that the value of the quadratic form at that vector is 0. So the quadratic form must have a non-trivial 0. Alright, so let's see why these are equivalent. Now, one direction is obvious because if V is isometric to the hyperbolic plane, in the basis say V and W, then what does that mean? That just means here that Q of V in particular is 0, and we get bonus also Q of W is 0. So V got some isotropic vectors. Now let's look at the other direction. So suppose that V is isotropic so that we can actually find some non-trivial 0 of the quadratic form. Why is it that V must be isometric to the hyperbolic plane? Now, here we use the previous characterization. We are going to show that the discriminant of V is minus of a square. Well, indeed, let's just extend V to a basis, right? So, with respect to this basis, what is the gram matrix of the bilinear form on V? Well, this entry here should be Q of V, so it's 0, right? And so the discriminant would be 0 minus this, which is a square. So this is congruent to -1. And thus, discriminant of V is minus of a square, so V must be isometric to the hyperbolic plane as claimed. Thus, we have shown that a binary quadratic space is isotropic if and only if it's isometric to the hyperbolic plane. And here, observe that if the hyperbolic plane has this gram matrix with respect to this basis V comma W, then we have found two isotropic vectors, namely V and W, and actually this accounts for, their span account for all the isotropic vectors of H. Of course, we need to delete 0 from their span, but these two lines minus 0 are the set of all the isotropic vectors of H. So H has two lines of isotropic vectors.